Welcome to Phantastic Physics. Today I'm going to use this device to fire one metal marble straight out horizontally from this contraption, and at the exact same time this other metal marble that is exactly the same mass and the same dimensions will be dropped vertically straight down. So I have one firing horizontally straight out and the other being dropped vertically, and those events will happen simultaneously. So when I initiate this action, my question to all of you at home is, which steel marble will hit the table first? Will it be A, the marble that launches out horizontally, B, the marble that is dropped vertically, or C, will they hit at the same time? So take a moment to think about that, and we'll figure out what the answer is in just a moment. So before we find out what the answer is to our question, I'd like to remind everyone at home that if you are interested in the topics discussed in this video, please click the description to this video below and select the link to our Phantastic Physics store. We offer a full year of high school physics curriculum, perfect for teachers, for homeschool teachers, for students, and for parents who want to give their kids a boost when it comes to physics. All right, so let's dive in. I'm going to get on this ladder here, and I'm going to climb up to the very top. Now there is a lever here, so when I flick this lever, these balls are going to, one will shoot out directly to the right, or I guess from your perspective to the left, and this marble will fall straight down or pretty close to vertically straight down. And so again, remember the question was, will this marble hit first? Will the other marble hit first, or will they hit the desk at the same time? So here we go on 3, 2, 1. All right, so to see that, I think we're going to have to watch the footage in slow motion. So let's take a look. All right, so what did we just see? Well, it looked to me like both marbles hit the desk at the same time. Now, you could argue that the one that was dropped vertically maybe hit a fraction of a second before the other one, and I'm talking about the scale of milliseconds if you watch it in slow-mo. But I'm assuming that the reason that may have happened is because the mechanism actually released the balls at a slightly different time, and that could account for the difference. But if you do watch the video in slow motion, you could see the frame by frame shows that each marble was falling at exactly the same rate. So in theory, or technically speaking, they should have hit the desk at the same time. So why did they hit the table at the same time? Well, it has to do with the independence of horizontal and vertical motion. And so what that means is, if there's a force pushing something horizontally, like we saw with ball B, that does not affect its vertical motion at all. So vertically speaking, neither ball had an initial force pushing it down. We can agree that they were both dropped in the sense of vertical motion, whereas ball B was pushed horizontally with some kind of force. And so if you looked at ball A, after a fraction of a second went by, we know that as it's falling, it's accelerating due to Earth's gravity. And Earth's gravitational acceleration has already been calculated long ago, and that is, we use the symbol G for Earth's gravity, or for its acceleration, 9.8 meters per second squared. And what that means is each second an object is in free fall, its velocity or its speed is increasing by 9.8 meters per second, or approximately 10 meters per second. That means if I drop something, after 1 second, it's moving at 10 meters per second. After 2 seconds, it's 20 meters per second. After 3, it goes to 30. So its speed, its velocity is increasing by this amount every second. Now, if I push something forward or throw something forward, that doesn't change this gravitational acceleration. So if I looked at marble B, after the same amount of time went by, well, instead of falling straight down, it's going forward. What I do know is its vertical speed is the same for both of these objects, because it doesn't matter if you're pushed forward or downward, or if you're just dropped, you're going to have the same vertical velocity because you're accelerating at the same rate. The difference is this marble also has a horizontal velocity, which is causing it to move forward as well. Now, going back to marble A again, after another fraction of a second goes by, it's moving faster, right? So instead of being this velocity, it's definitely increased because it is accelerating the whole time it falls. And if I looked at the other marble, the one that was shot forward, it's now maybe over here, but vertically speaking, it should be in the same position. right? It still has this forward velocity, which came from the initial push, but it still also has the same vertical acceleration as this marble. So because their accelerations in the vertical direction are the same, over time, they're still falling at the same rate downward. Even though this one has a horizontal velocity, it does not affect the vertical velocity. So if I were to trace the path of marble A, of course, it just goes straight down. And if I trace marble B, it goes along this sort of parabolic curve. But when I break their velocities into components, horizontal and vertical, you can see that the vertical component of their velocity will never change for any objects that are released, regardless of whether there's a horizontal force or not. So that is the reason why both objects hit the desk at the same time. So one additional application of this phenomenon, the independence of horizontal and vertical motion, you can take a bullet, so take a handgun and fire a bullet completely horizontally straight ahead, and at the same time drop a bullet. And it doesn't even matter if the bullets have different masses, because we know things fall at the same rate anyway. But the one that's shot will fall at the same rate vertically as the one that's dropped. And actually Mythbusters did this experiment already, and they were able to prove that the dropped bullet and the shot bullet still hit the ground at the same time, even though that bullet is traveling a much greater horizontal distance. That doesn't change the vertical motion of that bullet. Now, of course, that result would change if you're firing around over a much larger distance. So for very long ranges, you now have to take the curvature of the Earth into effect. And when the Earth curves downward, that means there's more of a vertical drop for that bullet, which will change the results. And also you have to take air resistance into account, because over a great distance, that air resistance is going to have a noticeable effect on this experiment. But for short range, this shows that no matter what, you're always going to have two objects hit the ground first, whether it's dropped or whether it's shot with a horizontal force. It does not affect the result either way. Thank you for watching Phantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.